Hello everybody and welcome to the University of Birmingham's Extreme Robotics Laboratory. My name's Faye McCabe and I'll be hosting our live stream today. We're really excited to share with you all lots of different technologies that we're going to combine and use to perform a simulated search and rescue task. So we've created a simulated disaster zone in the laboratory and I've hidden something there for our semi-autonomous robot, the Husky, to find. And the Husky can either be controlled remotely by an operator and it can also make its own navigational decisions if the operator is distracted or busy with another task. So we're going to see that. And we're also going to see how we've created a 3D scan of the lab that can be explored using virtual reality technology in order to kind of strategize and safely plan a route in the disaster area. So first, we're going to be hearing off my colleague Manolis, who's going to give us a nice overview about how humans and robots can work as teams in extreme environments. So over to you, Manolis.
All right. Hello, everyone, and welcome. Basically, I'm a research fellow here in the Extreme Robotics Lab. As Faye said, my name is Manolis, and I'm going to show you and actually give you a bit of motivation for the demo you're going to see in a bit. So we care about sending robots in dangerous and difficult and hazardous environments, mainly to keep humans from harm. So by sending robots first, we keep humans safe. Instead of sending humans, or by sending humans after the robots, we can keep them safe. And basically, you can imagine environments after some kind of catastrophes, like earthquake or some kind of nuclear disaster or some other environments like that. And we send the robots there to do some tasks. And these tasks might include mapping the environment and find any potential hazards to notify the human teams. Perhaps manipulate some objects or move some objects in the environment that they are difficult for humans to handle. Or conduct a search task, an exploration task to find some victims in the environment. And in today's demo, we're going to focus on robots that they are ground robots. Obviously, we can send drones, we can send underwater robots, but for the demo today, we're going to have a ground robot. And the typical setup looks like that. So normally, you have the robot in the hazardous area, and you have a human operator from a safe distance controlling the robot remotely, either by using some kind of joystick and a graphical user interface. And those robots mostly are either supervised or teleoperated. And you may ask why they're not fully autonomous. And that's a very good question. And actually, despite all the advantages in robotics, humans, they're very good in certain things, much better than robots. For example, a human operator can have critical or moral thinking, or a human is very good in dealing with situations. They are perhaps unpredictable. So that's why, ideally, we would like humans to collaborate with robots, and they form up a team. And that's why, basically, the demo we're going to see about is about human-robot teaming. So how humans and robots can collaborate to perform the tasks I mentioned before. And like to motivate this furthermore, basically, as you can imagine, if you are a robot operator in a disaster response and you want to help the rescue team, for example, it can be really stressful, and this environment actually are very difficult to drive the robot. So we can try and make the life of those operators easier. And there are like a couple of ways to do that, but let's focus on two for the sake of this demo. So one is to provide better information to the operator and improve something we call situation awareness. So basically the understanding that the operator has of the environment. And we can do that by better graphical user interfaces or multimodal feedback, or even with virtual reality, as we're going to see in the demo, and augmented reality. Another way to do that is by having robots having different levels of autonomy. So basically, a robot could not be just autonomous, but it can have different levels, which it can switch on demand. So perhaps if the operator is tired, the robot can take control and can help the operator. If the operator wants to do something else and the robot is not aware of, the operator can perhaps directly take control of the robot and teleoperate it. And you can imagine that this is something similar to autonomous and semi-autonomous cars, in which, in a sense, like an autonomous car is a robot. So you can imagine, like, if you have a driver and is tired or is not following the lanes in the road, perhaps the car takes over and the lane assist system. And similarly, if you are in an open highway and everything is fine, the car can drive itself, right? So you can think of something similar like that. And actually, without any further delay, let's go to the demo.
Hi, my name's Dr. Christopher Bibb. I'm a research fellow at the Extreme Robotics Laboratory, and my field of research is mainly in human factors, human-computer interaction, and human interface technologies. So really what all that means is the best way for the human to interact with the system or the robot. So a lot of this includes things like data visualization, what's the best way of displaying lots of different types of data and sensors, as well as the best methods of system interaction. So within VR, this can include things like hand tracking, controllers, and eye tracking. So I'll jump right into the demo. So as you can see on the table includes what is a simulated holographic display. So this essentially means that we're using VR to simulate what a volumetric table could look like. So we can see the hands, and then you can interact with the table using hand tracking. So you can zoom in and out by stretching your hands. You can rotate the table by putting it along the edge of the table, and then drag and move the table. So if there's been a disaster, the first thing you might want to do before sending rescue people or robots into the building is have a look at what existing data sets there are. So the really most basic form of this might be floor plans. So if you bring the floor plan onto here, you can see that this has been as overlaid onto the table. You can inspect it, you can zoom in and out, and you can have a look. But 2D data like this, there's no real need to view this in VR, whereas you can bring in 3D data of survey data, for example, such as using Matterport scanners. So as you can see on here, we've got the 3D model of the Extreme Robotics Laboratory on here. You can take away the floor plan and leave just the model now. And then on here, you can, again, zoom in and out, interact with it. So using this 3D model, you can see it all stereoscopically in 3D. You can interact with the map. You can have a look where the corridors are, where all the doors are. So you can interact with the map, and then this might be quite historical data. So this data itself could be a few years old, or it could be low resolution, so you can bring in newer forms of data. So after a disaster has happened, for example, you can bring in a drone to map the area, so you can bring in updated photogrammetry data. So photogrammetry is just making 3D models from video and photos. So as we can see on here, the photogrammetry data has been overlaid onto the historical survey data. And you can see, since the disaster, lots of things have changed. There's lots of new things around the area, such as the rubble and things like that. So with this, you can use the system to try and identify things automatically, such as targets that the robot might want to look at. So you can see here, we brought up the targets. Each one of these spinning red circles indicates what the system might think is something worthy of inspection by the robot. And then you can bring up each one of these targets and have a look at it. So for example, here's some rubble. So the automatic target recognition has suggested this is a target to look at. It has a high probability that that something is there. So on here you can see there's a 3D model, you can inspect it 360, and then you can get more information out of it. So the next thing you might want to do is try and plan the path of the robot. So on here you can see that the system has automatically planned a path for the robot to take through the area, and then this will ensure that the robot has a look at all of the different targets that have been suggested, as well as perform an optimized path through the system. And this so far has mainly been used for planning. So with this, we brought in lots of historical data, some newer data, different types of data from scans and drones and floor plans, but you can also bring in live data from the robots. So on here we can bring up sensor data directly from some of the robots. So you can see up here now that there are 3 different types of data that can come from the robot. There's depth data that shows 3D information. There's infrared data, again, that can also indicate depth, and then just normal color imagery. So these 3 different types of data put together can allow the robot operator to see what the environment is, but it doesn't provide the high level overview that a supervisor might need to try and give instructions to a fleet of robots. And this can apply equally to a whole fleet of robots or land, sea and air vehicles that can be sent for inspection, and it doesn't necessarily have to be a single robot. So this supervisory control station can be used to give information to the robot operator and the robot operator can choose to follow their path or follow their own path, either autonomously or through manual control. So this has been a short virtual reality demonstration of being able to use lots of different types of data and visualize it all in one central place. So one single operator can have a look at the whole of the disaster space, as well as being able to give instructions to all the unmanned systems that are in the area. So now I'll pass you over to the robotic control demonstrator, and that will show how you can control robots both autonomously, manually, or a mix of the both, where you can pass off command between the robot and the human. Thank you for watching.
Hi, I'm Aniket. I'm a second year PhD student here at ERL, and I work on variable autonomy multi-robot systems. So in my PhD, I tried to understand how multiple robots, each with different levels of autonomy, can work together and carry out a task in extreme environments. And more specifically, I try to understand how a single operator can collaborate with a team of robots to carry out one task. So we've set up an exciting demo for you today, which combines all of the technologies that you saw before this. And before I actually take you through the demo, let me explain to you the robot that we're going to be using for the demo. So if you want to come with me, this is the ClearPath Husky robot. So the most prominent sensors, like as usual, we like to have multiple sensors on each robot, but in this robot we've got three main sensors. The first is the camera that an operator can use to understand a lot about the scene and get some situational awareness. We've got the UR5 arm. Now, while this is not going to be used in the demo, in most extreme environments, a robot uses arms or grippers like these to move debris, clear debris, or move obstacles from one place to the other, or assist stranded victims with some emergency first aid. And finally, we've got a laser scanner, which the robot uses to detect obstacles. And now we'll actually go back and have a look at the interface that we use to control the robot. So now I'll actually take you through the demo. If you want to just come and take a closer look, this is how a general interface looks like when we're trying to control a robot. Over here you can see the robot's camera, which I can move around with the joystick. You can over here see some of the stats of the robot, and here the map that we've generated with the LiDAR, and the robot's right here. And this is the interface that you use to give the robot a position to move to autonomously, or if you want, you can even teleoperate the robot. And these are the different levels of autonomy we discussed earlier. So in this task, we're going to try to spot an anomalous object in the environment. And this anomalous object could be anything. It could be a radioactive source, it could be a bomb, it could be anything which you can otherwise find in extreme environments. And we've hidden a dummy somewhere in this arena to mimic a trapped victim. And the robot's going to try and find these. Now, based on what we got of the VR scan of the area, the supervisors generally give us a suggested route that the robot should take, and the operators may choose to stick to this route or choose to deviate from the route a bit. So the first point we'll take the robot to is around here, because we should get a good enough scan of the whole arena, and the robot's going to try to navigate there autonomously. Okay, from here we can get a good enough look of the area, and we can move the camera to look for any suspicious objects which shouldn't be there. Looks like there are a few tires over here which do not show up on the LiDAR scan. So it's better to teleoperate the robot in this area. I'm just setting the camera straight. It's better to teleoperate the robot in this area because the navigation may not necessarily work the best manner. Oh, looks like we've spotted a victim there. If you just take a look. So we've spotted the victim. And around looks like there's something over there. It's a toy submarine. Well, thankfully it's a toy submarine. In extreme environments it could be something a lot more dangerous. But now that we've spotted the location of the anomalous object and the victim, we can give these details to the rescue team, and then they can carry on with subsequent rescue activities like helping the victim out and then retrieving the dangerous object. And then now that the robot has done its work properly, we can bring the robot back. So let me just recenter the camera. Right, so the robot's now found the victim and spotted the anomalous object. So now that the robot's done its mission, we can bring the robot back. So I'm just going to give it a goal back home. It's better if I take control of the robot and operate it around the tires because it couldn't locate them. But in such cases where I stop looking at the robot and talk to you about what's happening, I'm generally reporting to a supervisor, and the advantage is that we have some clever algorithms which can detect these exact scenarios and take control of the robot and move it back to the location it is supposed to move. Thanks for watching, guys. That's it for the demo. I hope you enjoyed it. I hope you enjoyed it as much as I did. So that's some of the technology we're working on, and hopefully this gives you a rough idea of how we put together aspects of different technologies and try to carry out missions in extreme environments. So that's it from us. Once again, thank you, and now we'll go to the question answer section.
Okay, thank you very much for that, Annika. We're going to host a question and answer session now with all of the experts you saw in the demo. We've got as well Chris Gall joining us today. So Chris Gall is the technical lead in the lab. So if you have some kind of hardware questions, that kind of thing, feel free to ask them. And you can also ask me a question. I realise I didn't really explain much about what I do in the lab, but I'm a third-year PhD student, and my research mainly concerns trust in autonomous systems and how we can display information to encourage appropriate levels of trust in autonomous systems. So let's have a look at the chat and see if we've got any good questions. Or I can see a really good one here that maybe for Chris Bibb. I'll just put it up on the screen. So can the 3D map be generated in real time, or is it based on already known blueprints? I'll just unmute you, Chris.
Sure, thanks, Faye. Yeah, that's a really good question. Things can be done both in real time and non-real time. So if you're trying to do photogrammetry, for example, which is just taking lots of pictures and creating a 3D model, then that's usually not real time. And it can be close to real time, perhaps a minute or two for a small data set, but most of that isn't real time. But you can have real time 3D scanning, such as using LiDAR or depth sensors. So you can have a mix of the two, really. But this demo was really trying to show that you can have the historical data, which would be floor plans, for example, and then you can have 3D scans of the building that could be done during construction, and then you can try and bring in real-time data, if you like, such as sensor feeds directly from the robot. So yeah, it's a mix of all, really. It can go from real-time to taking 1 minute to taking several days, depending on what type of data you like.
So do you ever think we will get through the ethical problems of full autonomy, or will we always need a human in the loop?
I think, Faye, best you answer it.
Yeah, I can give it a go. I'm a firm believer that we'll always need a human in the loop, to be honest. I feel that kind of robots and artificially intelligent systems have their place and they have strengths compared to humans, especially when it comes to kind of number crunching and dealing with high volume of data. But then humans have got imagination and kind of contextual understanding, and they can deal with kind of unknown situations and draw from past experience to deal with surprising and out of the ordinary situations, which is something that artificial intelligence can struggle with. So really, to me, I think the answer lies with interdependence between humans and with these artificially intelligent systems, and then we can complement each other's strengths and protect each other's weaknesses a little bit. We've got a question from Foul Body Autopsy. Can new robots withstand very high levels of radiation, for example, working on a nuclear disaster cleanup after a critical accident? Would anyone like to take that question?
Yeah, I can take that one. Although it's not our expertise about the electronics of the robots, but I think some other members of the National Center of Nuclear Robotics have developed the electronics that they needed to withstand these high levels of radiation. In here, basically in Birmingham, we mostly do the robots do smart things. So we don't design the robots, we don't design the electronics. We design the algorithm that makes these electronics do smart stuff. So I cannot completely answer your question, but I have a feeling that we have some kind of these sorts of robots.
So Xanadu King says, what is the technology status of robots providing advice to the human in search and rescue situations?
So it's a bit of a general question. So it's not as much about robots providing advice to humans in SAR situations as much as we would like to have AIs at the operator station taking the data that the robot gives us and then processing that to give advice to the humans. Because any advice that a robot gives to the human, it's important that the robot finds a way to use it itself. So that's the first thing. The second thing is that we don't really want to put on the robot a lot of computational overhead for processing data and coming up with advice. So it's better we separate the advice from the robot, where we have the sensor processing and all the data crunching happening at the operator end, where we have AIs that are specifically giving advice to the operators and assisting task supervisors with advice, whereas the robots at as much as possible should focus on carrying out the task and intelligence required to help the task.
If I may add very, very quickly on that, so about the current status of this kind of robots, so I think most of them, they have deployed in this kind of scenarios, they're mostly teleoperated. So it means they don't really have a lot of autonomous capabilities. And even if they do have, the industry doesn't use them because they are very conservative, and for a good reason. You know, if anything goes wrong, I mean, you have to have a very, very robust robot. But that's why we're here. We try to make these robots more intelligent, as Aniket said.
And let me just have a look. So Constant Disappointment's got a really good question here, maybe for Chris Bibb. So he says, what VR hardware/software are you using? And is any of it built in-house? So if you want to take that, Chris.
Yeah, sure. Thank you, Faye. So most of the software and hardware that we use in the lab is commercial off-the-shelf stuff, but we do a lot of prototyping as well. So, for example, if we were trying to convert a VR headset to be AR, then we can create our own camera system and then write our own software so we can have accurate augmented reality overlay. So, yeah, it's really a mix of the two, but a lot of the research that we do can be built with commercially available tools.
Oh, we've got another one from Constant Disappointment as well about the Husky robot this time. Let's have a look. Is the Husky used in the real world? What problems does it encounter in a non-lab environment? And what do you do if it gets stuck? So who would like to take that question?
I can take that. So thanks for the question. Very interesting question. Actually, some of the work I'm carrying out in my PhD addresses this specific problem. So yes, we do use robots like the Husky in a non-lab environment. And we generally hope that it doesn't get stuck. And in my PhD, I'm trying to look at different situations in which Husky robots or any UGV robots are likely to get stuck. And there are a set of parameters that we can study sometimes to detect situations where a Husky is likely to get stuck, and then avoid them well in time if their situations are detected and we have clever AIs helping us out. And if we want to just answer Jackie Cruz's question as well, that's pretty much why we have a human in the loop, because an operator has the experience of using robots in such environments, and hence he or she can use his expertise in detecting the situations and avoiding them well in time.
Has anyone got anything to add to that one?
Yeah, since people are typing their questions, I can elaborate perhaps on that. So as Aniket said, we benefit from the human expertise if we have a human in the loop. So basically, humans, they have a different set of capabilities than the robots. And these kind of environments, they're very unpredictable, if you wish. So humans can deal well with unpredictable circumstances. Robots, not so good, despite the advantages. And also there are some other questions which are a bit more on the moral side. So if we have a human in the loop, it can detect the victim and can decide if the victim, like the best approach, for example, to save a victim. Are we ready to leave this kind of advice to the robots? Well, like as an example.
Could you also use augmented reality for SAR?
Yeah, so augmented reality differs really from virtual reality in that virtual reality, you're fully enclosed and you can't see the real world, whereas augmented reality, you can also see the real world. So VR really, within robotics, has a strength in teleoperation, like I was saying before, whereas augmented reality is good at overlaying information. So if you're away from the robot, for example, you're operating it from a safe distance in a dangerous area, then VR might be more practical, whereas AR is good if you're actually there on the scene and you're trying to overlay information. So it could be that VR is used before anyone goes into the building, and then AR is used when someone goes in and to give them further information.
Denise English saying, question to the two Husky guys, what is mixed initiative control? And there's actually two questions here. And what else do you do in the Extreme Robotics Lab? So I don't know if the Husky team want to give that one a go.
Sure. So mixed initiative is basically, okay, let me break it down a bit more elaborately. So in the demo, we talked about the different levels of autonomy that can be used in the robot. So for sake of simplicity, let's assume that a robot has two levels of autonomy. It can work autonomously, in the sense independently without any operator command, and it can be teleoperated. So the question is, someone has to make the decisions as to which level of autonomy a robot would use at any given point of time. And usually the teleoperator or the supervisor, along with guiding the robot and planning the task, takes charge of switching between the levels of autonomy. And this is called a human initiative system. If we have an AI or an algorithm in charge of switching between the levels of autonomy, that's called an AI initiative or a robot initiative level of autonomy switching system. And most of the times what happens is we have an AI that is capable of judging when a level of autonomy switches have to be made to protect the robot and the hardware, but operators are more aware of the mission and the tasks and are more mindful of how adversities and new information can change the mission. So we need both of them to have the level of autonomy switching capabilities. And when both an AI or the robot and the operator can carry out level of autonomy switches together on the same system, it's called a mixed initiative control scheme. So that's the first question. And the second question, Manolis, I think it's better if you answer it.
Yeah, sure.
If you want to step in.
Sure, it's quite broad, but we do a variety of stuff. So to continue from Aniket's answer, in this kind of system, another thing we check is if the autonomy can trust the human operator, if the human operator can trust autonomy, and perhaps Faye can elaborate a bit on that. So because it's here research topic, other stuff we do in in the lab is autonomous manipulation. So we have some manipulators with computer vision, so some robot arms basically, and we check how they can grab obstacles and objects in a reliable manner. And basically, actually, a lot of work we do with this kind of robots involves a variety of disciplines. So we're quite multidisciplinary. So we have AI, we have human factors, we have human-robot interaction. So we do a variety of things. So if Faye wants to continue about the human factors, perhaps better, and then the trust in systems.
Oh yeah, thank you, Manolis. It actually leads really nicely onto this next question. So I might just put that up on the screen, which says, what is required to trust autonomous systems? So that's an area which I've kind of focused my research on. And the thing that I've kind of realized the most is transparency is really important to trust in autonomous systems, because if you've got a system where you don't really understand how it works or why it works, and it's giving you an answer, that answer may be correct, and maybe it's really confident that it's correct, but unless you've got some way to kind of unpick that and really understand the thinking behind it and why it's coming to those decisions, then how can you really trust that outcome, especially when you consider that kind of autonomous and artificially intelligent systems, when they're dealing with kind of surprising or new kind of sets of circumstances, they may not really know how to react. So it's important at all times that we really understand what they're doing. So in the trust literature, we talk a lot about the 3 Ps of a system, which is the process, the purpose, and the performance of a system. And by making those crystal clear to the operator and giving them a really in-depth, thorough understanding of why something's doing what it is and why it's come up with the answer that it has, I think that's what we really need to foster trust in autonomous systems. I've got lots and lots of questions here. Oh, there's a good one from Constant Disappointment. What other cool machines do you have apart from the VR stuff and the robot and the Dalek? So would anyone want to answer that question? Maybe Chris?
Yeah, I can jump on this one if you like.
Thanks.
Okay, so most of the robotic systems we've got in the lab are off-the-shelf robotics. So we've got a bunch of KUKA arms. Some of them are industrial grade. They're designed to just be sat in an automated manufacturing environment, for example. Then we have some that are called cobots. These are designed with built-in force sensors, and the housing is designed so there's no kind of dangerous edges to them. They're meant to be safe around people, so you can work alongside them. They're quite interesting. We've got Frank arms, which are very similar, but the low payload. You can directly manipulate them to teach them movements. As far as the actual engineering side, we've got a bunch of 3D printers, a mini lathe, pillar drill, that kind of stuff. So if there's any equipment that the guys want making for their projects that don't exist, I can help them build it and put it together and get them integrated on the arm. One example is this little cutting wheel I designed to go on the end of an arm for one of the automated cutting systems that one of the guys are developing. That's the main gist of it. I still think the Dalek's possibly the coolest robot that we've got there.
Okay, thank you very much for that, Chris. Thank you. And then Foul Body Autopsy has a very timely question, as it's International Women in Engineering Day. So happy International Women in Engineering Day, everyone. And he says, or they say, as it's International Women in Engineering Day, who are your favourite female engineers? So I could kick us off with that one. I don't know if anyone else got a favourite, but mine, the first one that springs to mind for me is Margaret Hamilton. Now, Margaret Hamilton worked for NASA and she took us to the moon, and it was before the days of fancy code compilers. So she actually hand typed the code that took us to the moon. It was nearly 6 foot tall, stacked on each other. And there's a really famous photograph of her standing next to the code, and the code is actually taller than her. But I've got great respect for all the women in engineering, especially the ones that were around when maybe things weren't as equal as they are now. So yeah, thanks for that question. Really great. If anyone else has got one to add, feel free.
Yeah, so basically, like someone already guessed, but part of our work is inspired by Professor Robin Murphy and all this disaster response robotics, like speaking about more modern women in science. So yeah, she has been quite an inspiration for a lot of the disaster stuff we try to do here.
Okay, Mo Kebab asks, what do you see robots doing in, say, the next 50 years? If anyone would like to answer that one.
Okay, yeah,
Anybody?
sure, I can answer that. And the answer is we don't know. So, like, we are not prophets, right? I mean, definitely we are going to see robots more and more in a variety of tasks in our everyday lives, but we really don't think we can predict with accuracy what is going to happen in the next 50 years. I mean, robots already do amazing things, and we will keep seeing them doing even more amazing things, but who knows?
If I can just come off the back of that, Manolis.
Sure.
So, again, it's very difficult to tell where things are going to go as far as, how intelligent robots are going to become and how intelligent we're going to allow them to become, because there's a lot of, questions that people ask morally and ethically, etc. But as far as the way mechanically they advance, I mean, if you look at robots from 20 years ago, the small arm that you saw on top of the Husky can take about 5 kilograms. About 20 years ago, a robot that could handle 5 kilograms would probably be about 4 or 5 times the size of that. So just with the advancements of our mechanical systems, things are going to get smaller and more compact and less bulky and easier to install. So outside of the autonomous systems, just in general, things are going to get a lot more easy to use and easy to install. Hopefully that helps.
So in your Husky, although you mentioned it won't be used in the demo, will the articulated robot be able to work with the mobile base when in motion? Are there any inverse kinematics considerations?
Actually, that's a very good and difficult question. So we haven't tried that yet, but we have some experts in manipulation in the lab that we plan to do some kind of mobile manipulation in the future. So I don't know if it's going to work or not. I mean, we can move it probably, but I'm not sure if we can move it to do something meaningful. But that is going to be work in progress. But like no one in here at the moment is one of the manipulation experts in the lab, so we cannot like fully answer your question. I'm sorry.
Just to add to that, if Kartikeya Walia, if you want to just Google and look up the work of Tommaso Pardi, he does a bit of work on how you can use the arm on the Husky to carry out tasks.
I think we've got some Terminator-related questions as well. Hopefully that's not going to happen anytime soon. We're definitely not building Skynet in the ERL, just to assure you all.
Officially.
Officially, yeah, that's the official word on the matter. So.
You'd be surprised how far away robots are from being that intelligent. If you actually saw how simple some of the systems are, yeah, we're a long way from having to worry about that.
Okay, well, it's looking like we're about to run out of time. So I'd just like to take this opportunity to thank everybody who tuned in today and watched us and asked questions. You were all really great. What a fabulous audience. And thank you to all of my colleagues who I know have worked incredibly hard over the last few months to put this together. I think it's been a great day. And can we also take this time to thank the organisers of the Festival of Robotics and UK-RAS for giving us this chance to showcase our work to the world. And the last thing I'd like to say is happy International Women in Engineering Day. I hope you've all had a fabulous one, and big respect to all the female engineers out there and all the roboticists out there too. So thank you very much, and I hope you enjoyed our live stream today. Thank you.
Thank you guys. Bye-bye.
Thank you, everyone.
Thank you guys. Bye-bye.
Bye.